We just discovered when connecting a source to a load via a length of transmission line that the ideal case occurs when the source is a quote match source. Its load source impedance is numerically equal to the characteristic impedance of the transmission line to which it is attached. Likewise, in addition to the match source, we have a match load. The load impedance is numerically equal to the characteristic impedance of the transmission line to which it is matched. In the case where we have both a match source and a match load, lots of good things happen. Because we have a match load, there is no reflected power. Because we have a match source, the incident power is equal to the available power of that match source. As a result, the net power flow along the transmission line is equal to the available power minus zero, or the available power, and since that's the net power flow, it is absorbed by the load. In other words, for the special case where the load impedance is Z0, numerically equal to Z0, source impedance is numerically equal to Z0, and the load impedance is numerically equal to Z0. For that special case, then all of the available power of the source is delivered and thus absorbed by the load, the quote-unquote maximum power transfer. The important point of this is that's all true regardless of the length of the transmission line. If I have a match source and a match load, I have maximum power transfer. I have a conjugate match that exists for any and all lengths of transmission lines. Well, that's all well and good, of course, but the question is, how often do we have this ideal case? I've talked more than once about the fact that this model that we have, that we're analyzing, is not a simple academic model. We're not just lumping or soldering some lumped element here at the load and soldering some voltage source in series with a lumped element impedance here on the other side of the transmission line. Rather, this is the equivalent source, the equivalent circuit to some very useful, expensive, and elegant piece of electrical engineering, a component, system, some linear time invariant device, which we have replaced with its equivalent circuit. Same thing here for this load. It's the input impedance for some very useful, elegant piece of electrical engineering that the other side of the transmission line is attached to. We're using the transmission line to get energy from one useful device or system into another useful device or system. And so we ask ourselves, what's the probability then that since we design a useful system over here, it'll just happen to have output impedance that's numerically equal to Z0, or that the load here will just happen to have a input impedance that's numerically equal to Z0. It seems unlikely that we're going to have this special condition ever occur. In fact, it seems unlikely that we'll ever have a conjugate match occur. When you think about the maximum power transfer, we need a conjugate match. And that depends on, of course, the source impedance, and therefore we need the input impedance of the transmission line to be the complex conjugate of ZG. But the input impedance of our transmission line depends on the load impedance at the other end of the transmission line, that load impedance that's terminating it, the characteristic impedance of the transmission line, and of course, most importantly, the length of the transmission line. It seems very unlikely that these four things would come together to give us a conjugate match. And under the condition that we sort of have an arbitrary source impedance and load impedance and transmission line length, not only will we not have a conjugate match, we probably will have a set of source and input impedance such that the amount of power delivered by the source will be far less than that available from the source. We'll be nowhere near maximum power transfer. The question then, is there any way to fix this problem? If you recall, we had a similar problem earlier in the class where we were talking about attaching a source directly to a load. And when we had, for the same reasons discussed earlier, the source impedance and the load impedance were not related by a complex conjugate. Do we just accept the fact that the power absorbed by the load is far less than the power available from the source? Well, our solution was to go through and drop between the source and the load a lossless two-port device that we called a matching network. The matching network transforms our load impedance into a new impedance that is the complex conjugate of that source. Again, a matching network is lossless, but lossless networks are not, generally speaking, matching networks. A matching network is a specific kind of lossless network, one that's designed to transform a specific load impedance into a specific input impedance. The question then becomes, can we use a lossless matching network to fix our problem with the transmission line? Again, before we dropped the lossless matching network between the source and the load, but now we already have a transmission line that is connecting the source and the load. Well, it turns out we can go through and cut the circuit into two pieces and then insert the lossless matching network in between those two pieces. For example, we could drop the matching network here between the source and the remainder of the circuit, the terminated transmission line. The job of this matching network is to transform the input impedance of this terminated transmission line, its value, transform that impedance, that input impedance, into a new impedance, which is the complex conjugate of our source impedance. And so by doing so, we establish a conjugate match at this port plane. Looking to the left, we see a source whose impedance is ZG. Looking to the right, we see a one-port device. And the input impedance of that one-port device is the complex conjugate now of ZG, if this matching network is properly designed. Again, I emphasize this impedance is the equivalent circuit for this entire one-port device. This is not the input impedance of the lossless matching network. It's not the input impedance of the lossless matching network and connected to a transmission line. It's the input impedance of the one-port device, which is the lossless matching network connected to the transmission line, which is terminated in a matched load. This one impedance comprehends this entire structure, two lossless two-port devices, the matching network and the lossless transmission line, with the load terminating it at the end. One other important point to make here, and we'll make it again later, is that we've established a conjugate match here. It turns out we've likewise established a conjugate match at this port plane. If we were to go through and determine the equivalent circuit looking left of this port plane, and again, we can look at the matching network now as a source transformer that transforms the original source into a new source with a new source impedance. Likewise, we can think of the lossless transmission line as a impedance transformer that transforms a load impedance into a new input impedance here. If we have designed this lossless matching network correctly, we will find that the source impedance of that is the equivalent of all of this, its output impedance, and the input impedance of everything looking to the right, the input impedance of this terminated transmission line, they will be related by complex conjugate match as well. Further, if I were to go through and draw a line right here, take this port plane, we could come up with an equivalent circuit of everything looking to the left. We take the original source and it's transformed by the lossless matching network into a new source, a new equivalent source with a new source voltage and a new output impedance. But then we can view the transmission line as another source transformer, which transforms our transformed source into yet another source that replaces everything to the left. And so we have another transformed source here connected to our load in our equivalent circuit. And what we find, if we have designed this matching network properly, is that the load impedance here is the complex conjugate of this transformed source. If we establish a conjugate match at one port on our one port plane, we have established a conjugate match at every location. This is true if we have filled the space between our original source and our load with lossless networks of any kind. If we've established a conjugate match at one location, we've established it at every location. We could go through and take a saw and cut right through the transmission line at some point, some index Z, and separate this like a magician separating, someone saw it in half, and replace everything to the left of whatever location is with an equivalent source, and replace everything to the right with its equivalent input impedance. And what we find is the input impedance looking to the right and the output impedance looking to the left is likewise related by a complex conjugate match. One is the complex conjugate of the other. And again, that's true if we've designed this matching network properly. Once we design a matching network to establish a conjugate match at one location, we have established a conjugate match at each and every location within this circuit. Again, this is true as long as the devices between the source and the load are all lossless, and clearly they are in this case, a lossless matching network and a lossless transmission line. So do we have to put the matching network between the source and the transmission line? Well, it turns out we could just drop it on the other end of the transmission line, cut the circuit between the end of the transmission line and the load, and put a matching network there. What is the point of this matching network? Well, we want to go through and transform ZL into a new impedance, the input impedance of the structure, a value which will be equal to the complex conjugate of the new equivalent source looking to the left. We can view this transmission line as a source transformer that will transform our original source into a new source with voltage V out and source impedance Z out. And we want that impedance Z out to be equal to the complex conjugate of the input impedance of this structure. We want to transform ZL into an impedance whose value is the complex conjugate of the output impedance, again, which is the transform source. To here. We're not trying to make the input impedance equal to the complex conjugate of ZG. Remember, when we transform this source, we come up with the equivalent circuit here. Z out will be different than the original ZG. We want to design this such that Z out is the complex conjugate of whatever the input impedance is. And remember, that input impedance is not going to be equal to ZL. Once we've done that, we've established a conjugate match at this point. And because of that, we have a conjugate match at all points. And so let's go back here to the beginning. We have a conjugate match that would be established right here. If we've done our matching network design properly, we'll find the input impedance now to this remainder, this equivalent circuit. Here's our port plane. Everything looking left can be replaced with one equivalent circuit, an impedance of value, which is the input impedance of all of this. If we've designed our matching network properly, the input impedance will have a value which is equal to the complex conjugate of that source impedance. There will be a conjugate match right here. Because there's a conjugate match right here, we know all of the available power of this source will be delivered. All of the available power, thus, will be absorbed by the input impedance of this structure. In other words, we're saying all of the available power of the source is going to be absorbed by everything to the left, by this single port device. Now the question is where in the single port device? But we know what that answer is, because the lossless transmission line is lossless. It can't absorb any of the energy. The lossless matching network is lossless. It can't absorb any of the energy. So any energy absorbed by this entire structure must be absorbed entirely by that load. So the available power of the source is absorbed by the input impedance of this structure, meaning that's absorbed by the entire structure. And for this particular case, because the lossless devices, meaning it must be absorbed by the load. All of the available power of the source is delivered and ultimately absorbed by the load. That's what we're trying to do to deliver the maximum amount of power to that load. I want to emphasize, therefore, and I've said before, once we establish a conjugate match at any point within this circuit, we have established a conjugate match at all points within the circuit. I could go through and cut the transmission line in half and come up with an equivalent source looking to the left, a Thevenin's equivalent source. I could then go through and determine an equivalent circuit looking right, the input impedance looking right. And if we have designed our matching network properly, we'll find that they are related by a complex conjugate. So if we have a situation where all of the available power is absorbed by a load, and the networks between the source and load are lossless, it means that there is a conjugate match at any place and all places. Or if we have a conjugate match at one place, we know we have a conjugate match at every other place, and we know that all of the available power of this original source is going to be delivered and thus absorbed by this load. All right, so again, if all available power is absorbed by the load, I have a conjugate match anywhere and everywhere. If I have a conjugate match anywhere, that means I have a conjugate match everywhere, and it means that all of the available power is absorbed by the load. So in problems that I give you, I may say all the available power of the source is delivered to the load. Right away you know, oh, there's a conjugate match everywhere. I might say there's a conjugate match at this location. Well, then you know there's a conjugate match everywhere, and you know that all of the available power of the source is delivered to the load. So there are lots of bells go off anytime I say all the available power of the source is delivered to the load, or there's a conjugate match at one location. Now, also in problems, I will do tricky things where I will say, oh, the input impedance looking this way is equal to, 20 plus J30. Then I'll say, well, what is the source impedance of the equivalent source looking the other way if all of the available power of the source is delivered to the load? Well, there must be a conjugate match, and if this is 20 plus J30, the equivalent input impedance looking to the right, then the source impedance must be 20 minus J30, the complex conjugate of that input impedance. And I do this frequently. I will tell you what the impedance is looking this direction, and then I will ask you what the impedance is looking that direction. And if there's a complex conjugate match at one location, you can assure that the relationship is a complex conjugate match at this location as well. Or if I tell you that all the available power of the source is delivered by the load, again, there's a complex conjugate match anywhere and everywhere. I tell you what the impedance is looking one direction, you immediately know the impedance looking the other direction is simply the complex conjugate of the first. So you might ask the question, which method should we choose? Should we drop our lossless matching network between the source and the input of the transmission line, or should we put it between the output of the transmission line and the load at the very end? Well, we just showed that the two are equivalent. Either one will work. Every one, it's 6 one, half dozen of the other. But it turns out we do neither of them, generally speaking. In radio engineering, our solution is not to insert one matching network, but in fact to insert two matching networks. We put one between the source and the input of the transmission line, and we insert another between the output of the transmission line and the load. Now, why do we do this? One of the things that happens when we have two lossless matching networks here is all of a sudden the number of degrees of freedom in our design space gets very large. We can go through and have any number of design solutions which will establish a conjugate match at one place and therefore every place. For any arbitrary lossless network I drop in here, I can come up with a matching network that will establish a conjugate match here and everywhere. Or if this is an arbitrary lossless network, I can design a matching network then to establish a conjugate match at one place and therefore at every place. So we have a multitude of solutions there since we dropped two of them. It allows us essentially double degrees of freedom in our design. And that is really why we add two of them, because since we have all these degrees of freedom that will satisfy the conjugate match solution, what we do is pick the one that is optimal for a reason other than simply it provides a conjugate match. So let's look at that. So the first matching network between the source and the input of the transmission line, its job is to transform whatever source and source impedance we have here to a new source whose source impedance is numerically equal to the characteristic impedance of the transmission line to which it is attached. In other words, it is to create a quote-unquote matched source. So if you look at the two-port device here, you could argue that this really isn't a matching network per se. In this case, it is simply a lossless two-port device that does a source transformation such that the output impedance now is numerically equal to Z0. What is V out? Well, V out is whatever V out has to be to satisfy this condition that Z out is equal to Z0. And as long as we have any kind of resistance in ZG, any kind of non-zero real part, we can always design a two-port device which will create this quote-unquote matched source, a source whose characteristic impedance is equal to Z0. And again, remember, there are lots of things that are pleasant about having a matched source. Foremost among them is that the incident power can be directly determined without knowledge of the load. We know that if we have a matched source, that the incident power is equal to the available power of this quote-unquote matched source. Again, this has nothing to do with conjugate matched. Matched here means only that the output impedance is numerically equal to Z0. For the second matching network in our circuit, the one between the transmission line and the load, we're going to design it such that it transforms the load impedance, whatever it is, to an input impedance that's numerically equal to Z0. In other words, we're going to transform the arbitrary impedance ZL into a quote-unquote matched load, a load whose impedance is numerically equal to the characteristic impedance of the transmission line that it terminates. We can always design a two-port device that does this as long as ZL has some amount of resistance, some real part that is non-zero but finite. We can always transform it into this situation. Again, a matched load does not mean we have a conjugate match. But there are a lot of good things about having a matched load. We know that the reflected power, for example, is equal to 0. And so this is our design that we have. We design our first two-port network to transform a specific value of ZG to Z0. And we have to know the value of ZG to be able to design this transformation. If we change the value of ZG to something else, the transformer that we design will no longer be effective. It only will transform a source with some specific value of ZG into some specific value of Z0. So these, again, are not plug and play. You just can't buy one off the shelf and drop it in there. It has to be designed for your specific ZG and your specific characteristic impedance. Likewise, for this two-port device, this impedance transformer, it will transform a specific value of ZL to a specific value of characteristic impedance. Change the characteristic impedance, or ZL, your two-port device will no longer accomplish what you want. You have to design a whole new two-port device. So what we've done here is, again, used our ports to transform our original source into a quote-unquote matched source and transformed our original load into a quote-unquote matched load. So this may seem like twice the work involved. Instead of designing one lossless two-port device that we drop between the source or the load, we instead have to design two. And why would we want to do this? Well, by using two separate matching networks, we essentially decouple the design problem. If we have a single matching network, of course, we have to go through and match for example, a source impedance to an input impedance, looking into the matching network. And that input impedance will depend on the characteristic impedance of the transmission line, the load impedance, and most importantly, the transmission line length. We talked about this earlier in our design process. We want to match our source impedance, ZG, to an input impedance that depends on ZL, Z0, and transmission line length. The problem here is if we change our transmission line length, then we have to redo our design. Conversely, let's look at the situation. We have two matching networks, one at the source and one at the load. For the first matching network, or the first source transformer really, our design parameters are simply ZG and Z0. We're going to transform ZG into a specific value, the characteristic impedance of the transmission line. For the second two-port device, we're going to transform our source impedance ZL into an input impedance, which again is numerically equal to Z0. If we look at these values, ZG, ZL, and Z0, they were the same parameters that were used for the one-port matching network design. So what's the difference? Well, the difference here is what's missing from this list. Notice transmission line length doesn't make any difference. The only characteristic of the transmission line that's important with respect to these designs is the characteristic impedance. And so we have a design that will work not only for one specific transmission line length, it will work for any and all transmission line lengths. And again, those are the happiest words in microwave engineering. The design is independent of the transmission line length. Imagine the problems if you're trying to connect one device to another device and you have design for maximum power transfer, all the available power of the sources delivered to the load, and then some annoying mechanical engineer comes in and says, oh, we need to move these things 3 centimeters further apart, or we need to move them 2 centimeters closer together. Now all of a sudden you have to change the length of your transmission line. Your design is destroyed. You have to redesign a new 2-port matching network. But for this idea, where we have 2 independent transformers decoupling the problem, simply transforming ZG into Z0 and ZL into Z0, that is regardless or independent of the transmission line length. And so an annoying mechanical engineer comes in and says, oh, you need to put these 2 devices or 2 systems 5 centimeters further apart. Well, you just go get a new transmission line that's 5 centimeters longer and connect them together, and you will get precisely the same power transfer you did before. You will still have a situation where all available power of your source is delivered to your load. So I should point out and make clear this connection to what we talked about earlier with respect to the ideal situation of microwave engineering, where we have a matched source, quote-unquote matched source impedance numerically equal to Z0, connected to a quote-unquote matched load. The load impedance is numerically equal to 0 with some length of transmission line. There are all kinds of great things that happen in that case. 0 reflected power, the incident power is equal to the available power, and we showed, therefore, that all of the available power of the quote-unquote matched source is absorbed by the quote-unquote matched load. We have a matched source and a matched load, and in that case, and only that case, when we have both of them, not one or the other, when we have both, we have therefore established a conjugate match. Why do we know this? Well, if all of the available power of the source is in fact absorbed by the load, then a conjugate match must exist at one place and at every place. And we showed earlier that it does. Clearly, if we have a length of transmission line that's terminated in a matched load, we know the input impedance will likewise be equal to Z0. If the source impedance is Z0, then we have a conjugate match. The complex conjugate of Z0 is Z0. Or we can look at the transmission line as a source transformer and see that the length of transmission line transforms our original source into a new source, which is likewise a matched source. The source impedance is Z0. It's connected to a matched load, value Z0. Once again, we have a conjugate match. And so any way you look at it, we have a situation where all of the available power of the source, the matched source, is absorbed by the matched load. The great thing about this design solution is that is independent of the line length. So again, I always talk about students saying, oh, if I have a matched source, then I must have a conjugate match. No, that's not true. If I have a matched load, I must have a conjugate match. No, that's not true. But if you have a matched source and a matched load, then you have a conjugate match. All right, under that condition. Now, that does not mean you can only have a conjugate match if you have a matched source and a matched load. As we showed in this lecture, you can drop in a 1-port matching network and establish a conjugate match where neither the source nor the load impedance will be equal to Z0, but it will establish a conjugate match, and therefore all available power of the source will be absorbed by the load, even though neither the source nor the load is a quote-unquote matched source or load. This is the typical problem that we do in microwave engineering. We pick a standard characteristic impedance. 50 ohms is typically the design. And microwave engineers go through and they will transform their sources using a lossless network into a source whose output impedance is equal to 50 ohms. Or they will take a device and transform the input impedance into a new input impedance that is numerically equal to Z0. And then we can connect these devices of a length of transmission line with a characteristic impedance of 50 ohms of any arbitrary length. The key thing here is the engineer that transforms the source to 50 ohms and the engineer that transforms the input impedance to 50 ohms are two different engineers working for two different companies in perhaps two different countries and maybe even at two different decades. But wherever one device is designed that transforms the output impedance to 50 ohms, at whatever time, at whatever place, and we take the other device that has been transformed, the input impedance has been transformed to 50 ohms at whatever place or whatever time it was designed, we can take those two devices, a third engineer can buy each of those two devices and connect them together with a length of transmission line of any arbitrary length. If that characteristic impedance is 50 ohms, then we know maximum power transfer will occur. And that's how radio engineering works. Everyone more or less agrees to transform their port impedances to this value of 50 ohms, and then we can take components made by different engineers from different countries at different times in different places and connect them together with characteristic impedance 50 ohm transmission lines and get maximum power transfer and not have to worry about the darn length of that transmission line. This then is our ideal system. We take this source, which again is an equivalent source of some very useful, important, elegant piece of electrical engineering. When the engineer is done designing this, they will likewise add on a two-port device that will transform whatever source impedance they have into a new source with a new source impedance that's numerically equal to Z0. Or we might have another engineer, again, at a different company, at a different time, at a different place, and they design some elegant piece of electrical engineering. It has some input impedance that is necessary, but it's not equal to Z0. So they'll add a two-port device, an impedance transformer at the port to transform that input impedance into a new input impedance that is numerically equal to Z0. And therefore, again, a third engineer can buy this component, this system, and buy this system, and at some other place, at some other company, at some other time, that third engineer will connect these two devices together with some length of transmission line, characteristic impedance Z0, and that engineer will not have to worry about transmission line length. This is the general way that things are done in microwave engineering. And what happens is because this third engineer never has to worry about the length of the transmission line, sometimes that engineer is not really as excited as they should be about the fact that it's independent of transmission line length. They're not as appreciative, perhaps, as they should be as to why these port impedances need to be these characteristic impedances. Again, if these were arbitrary impedances for both source and load, then that third engineer would have to design their very own matching network, and they'd have to design it in a way that it was dependent on that transmission line length. So this is the standard thing. All of our devices in microwave engineering typically are designed to have a port impedance, if it's energy coming out, the output impedance. If it's a passive device absorbing energy, then the input impedance, designed such that it has the standard typically of 50 ohms, a 50 ohm transmission line characteristic impedance. Remember, 50 ohm transmission line has nothing to do with resistance. The characteristic impedance is a characteristic of a two-port device, a lossless two-port device that's nothing but a bunch of inductance and capacitance.